sharing the screen. Thank you, Vetta.
Okay. I will try to keep my video on. If there are problems with the connection, maybe I can turn it off because it's more important that you see my slides than that you see my video.
Okay, thank you.
So let's try it this way. Okay, so I hope that you can see my
presentation. Great.
My presentation. Okay, perfect. So thank you for the nice introduction, and thank you for inviting me to give this seminar today. I'm very glad. So I know maybe most of you are not so let's say familiar or expert in GRB physics. So I will give a very, let's say, broad overview of what we know about the gamma ray bursts and what we learned over, let's say, the past few years with high energy observations with several instruments. Actually, I will focus basically on Fermi, on the Fermi Space Telescope, which is the one you can see in this title slide, but I will also talk about recent very high energy observations by, for example, the HESS experiment, of which I am an affiliate member, but also the MAGIC telescopes. So I hope you enjoy this talk. So what are gamma ray bursts? So this is one of the most famous representation of what a gamma ray burst is. Short and sudden electromagnetic signals in the gamma ray band, which becomes the brightest source in the gamma ray sky for a few seconds. So basically here what you see on the right is the so-called light curve, so the increase in counts that, for example, a gamma ray instrument mounted on a satellite can see, the so-called trigger of your instrument. And on the left you have the sky, let's say in gamma rays, in galactic coordinates. So the brightest band that you see in the middle is our Milky Way. And you see, so the gamma ray emission during a very short time becomes really very dominant when you study this kind of sources. So where did it all begin? Actually, it began in the 70s. Well, actually, it even began before, because the gamma ray bursts were first discovered by military satellites in the 60s, but actually the first let's say publications were in the 70s, because there was some time needed to, let's say, overcome the problem of having military information. Then science gained the data set and started to do a first analysis of these serendipitous flashes that were believed to come first from nuclear explosions by, let's say, the satellites were looking at Russians doing probably so trying to explode nuclear bombs in the atmosphere, and they realized that the signals were not coming from the Earth and not coming also from the Moon, but they were coming from the sky. And so in the 70s you had the first publication of these events. And as you can see, what I wanted to highlight, because I want you to bring on a journey, let's say, from the energetic point of view, to try to understand the instruments that saw these events, and also try to understand what they are. So basically the first events were studied in the energy range, let's say in the keV to low MeV energy range. You see the Vela satellites were more or less between 200 keV and 1.5 MeV. So this, as I said, was the very first publication in the 73. But since then, we know much more. So let's jump a little bit to the conclusion of what we know now. So basically, what do we know? We know that GRBs are cosmological. We know that GRBs are produced by ultra-relativistic jets exploded from these cosmic explosions that I will tell you more in a second. And these ultra-relativistic jets that is emitted from this so-called central engine of the explosion that propagates in space in a collimated jet, as is shown in this in this plot on the right. So studying this kind of jets, it's clear that the material that is expelled from this explosion must have extremely high bulk Lorentz factors. There are two emission phases of gamma-ray burst. These emission phases are the so-called prompt and the so-called afterglow emission. So as I said, these events are very, very short and sudden, but what was found over the years is that apart from the short and sudden first explosion, which is the so-called prompt emission, then there is a much, much longer and weaker emission that is emitted, that is so-called afterglow, and that can last from minutes to hours to days, even months after the first explosion. As you can see on this slide, I highlighted that not all of these let's say, bullet points of knowledge that we know, that we now believe are properties of gamma-ray burst were found in the initial KV energy range. But most of these things were found studying gamma-ray burst also in other wavelengths. Okay, so now here I highlighted the optical, the radio, the GV. So basically the study of this kind of properties was possible not only studying the gamma-ray burst with, let's say, the initial instruments that trigger and that discover these events, but by other instruments, other telescopes, ground-based or space-based, that followed up these events and saw different properties at different times. Another extremely important property of the gamma-ray burst is that they come in two families. And this is basically the most important distinction between gamma-ray burst, long and short gamma-ray burst. So what are long gamma-ray bursts? Long gamma-ray bursts are believed to be single stellar explosions. So you have a very massive star in the, let's say, at cosmological distances, so an early star that basically collides, collapses, and in this collapse you have then the expulsion of this, the ejection of this very collimated jet that then, if it points in our direction, we are able to see. So a single massive star. So this is the first model. The second model for short gamma-ray bursts is slightly different. You don't have a single star, but you have two compact objects, two neutron star, and black hole. So you have a possibility of two, usually it's two binary neutron star, it's two neutron star that merge, and when you have the final merger, you have again the ejection of this collimated jet, giving rise to the gamma-ray burst. The division is traditionally at let's say at a time stamp of 2 seconds in the KV regime. So if you have events that are shorter than 2 seconds, you traditionally say these are short gamma-ray bursts. In the prompt, always the division. And if you have an event that is longer than 2 seconds, then you talk about long gamma-ray bursts. So there are many more properties, like there were studies to connect gamma-ray bursts with supernovae. There were many studies basically in the X-ray to try to understand the common behaviors and common trends, to try to understand the spikiness of the events, the fast variability, all of these properties, and so these are what we call nowadays so-called pillars of knowledge. So these are things, because most of the time we tend to say gamma-ray burst science is still a science that has many let's say things still to discover. In fact, we know a lot of things, and most of these are now solid facts. What I want to point to stress out again, because I think that this is really the important direction that astrophysics, astronomy is getting into in the last let's say 30 years, but also in the last few years, is that multi-wavelength observation of sources in general is always the key to success, to try to understand what is the meaning behind an observation, because a KV observation alone of a gamma ray burst would tell you very few information. While if you have a look at the source with over the whole spectrum, going from radio to GV all the way up to TV even, you can find the questions, build your models, and find let's say answers to open questions. And so the really important thing is the synergy between instruments and also in the community to try to answer all together these questions that may still be open. So what happened through history, let's say? So in the first, let's say 40 years, basically gamma ray bursts were studied by various types of instruments. Here they were haunted by the instruments, starting from Vela. Then another super important mission was the Compton Gamma Ray Observatory, which did most of the, let's say, the discoveries in the KV to MEV and also to GV band in the 90s. Then we had Beppo-Sachs, which was an Italian-Dutch mission to discover for the first time the afterglow, so the X-ray afterglow, after, let's say, the prompt emission seen in the KV. And then we have Integral and Swift that are, so Swift was basically dedicated to the study of gamma ray bursts that are multi-instrument missions that had several, Swift has several instruments on board in order to study a gamma ray burst in all energy ranges. So it has a KV MEV instrument, it has an X-ray instrument, it has an UV optical instrument. So it is possible to follow up directly with the same instrument an event, and then this helps obviously following up. These are, let's say, the energy ranges that are seen by this kind of instrument. If we want to move up, so to up in energy, we have to wait for Agile and the Fermi satellites. So Agile was a precursor, let's say, of Fermi. It is an Italian mission that was launched a few months earlier than Fermi. And they are both analyzing, so they are both observing the sky, let's say, starting from around 100 MeV up to the GeV range. What I will also focus about at the end of my talk is the very high energy regime. So at the very high energies, you need to go back to the Earth again, and you have Cherenkov telescopes. For example, the currently operative ones are HESS, Magic and Veritas. I won't go into the detail of, I'm sorry about this, of the functionalities of these kind of instruments. I hope that you are all familiar with this kind of instrumentation. And these obviously were also hunting gamma ray bursts for the last 15 years at least. Until recently, they were still, let's say, still hunting, but nowadays we know that they can, and they did observe gamma ray bursts. And then there will be, let's say, a looking to the future for new, let's say, new hunters for gamma ray bursts, like the Cherenkov Telescope Array project that I will just mention at the very end. So an important, a crucial point to understand how to put all of these instruments in, let's say, in collaboration and also in communication is the so-called GCN system, so the Gamma Ray Burst Coordinate Network. So basically, it's vital that if you have a trigger from a gamma ray instrument, you disseminate your position, your location, your the information that you have at the very beginning to characterize a trigger, and you send this information to the whole community, to all the instruments, ground and space-based, so to encourage the follow-up as fast as possible in order to catch as much as possible of the emission, because you have to imagine if you have a burst that just lasts 200 milliseconds in the prompt and then it's gone forever, you don't see it anymore. It's really mandatory to be on time, on target. So this is absolutely important. And for this, we have since many years this coordinate network that helps us keeping in contact. We have the so-called automatic notices that are sent via instrument by the different satellites to ground, and there is a whole automatized process. But we have also then the human in the loop producing circulars and announcing further, obviously further, let's say, analysis and results of your data. So what is interesting about gamma-ray bursts at higher energy? So going to high energy, so I always write H.E. to VHE when I want to, let's say, as an acronym for high and very high energies. So very high energies and high energies can be crucial to try to give, as I said, questions to answers to many questions, like what are the mechanisms still behind both emission processes, so in the prompt and in the early afterglow. So try to understand the jet properties, trying to understand what is the central engine, try to understand particle acceleration. So many of these questions can find an answer if you go and study also the higher energies. Obviously, you can use gamma-ray bursts also to probe the universe. You can study cosmological relation. You can do studies about EBL, because you can go at much deeper, much farther away than, for example, AGN. You can also do tests of fundamental physics. For example, we used photons from several gamma-ray bursts over the past year to study, for example, Lorentz invariance violation. We did it a couple of times over the past 12 years on the cover of Science with our Fermi Science, and in this case, I will talk about this later on. This was our most famous gamma-ray burst in 2013, so this was the cover of January of 2014, in which we discovered this extremely energetic, for the time, not anymore nowadays, but this was the record holder back in 2013, this burst that made the cover of Science. So the Fermi mission, I presume most of you know what it is. So it's taking data since 2008. We celebrated our 12th birthday a few days ago on the 11th of June. The Fermi instrument has two basic detectors on board. So the primary instrument is the Larger Telescope, which is a pair conversion telescope. And as I said, let's say the lower limit is around 100 MeV. We have techniques to study our photons, also to go lower in energies, and we arrive to 20, 30 MeV, and then you go up to more than 30 GeV. We can also go up almost to TeV energies to study sources. In general, obviously, the LAT telescope studies a lot of sources, blazars, pulsars, and whatever. Obviously, gamma-ray burst is one small part of the sources studied by the LAT. The instrument that was built and dedicated to the study of gamma-ray bursts is the GBM, so the gamma-ray burst monitor, which are 12 plastic scintillator detectors that are placed all around, as you see, these small scintillator detectors on the four corners of the spacecraft, and they monitor the keV to MeV energy range, so the energy range where we expect to trigger to find the gamma-ray bursts. It's an international collaboration between many universities and institutions around the world. Important for gamma-ray burst science is the field of view of these two instruments. The GBM sees most of the time the whole sky unocculted by the Earth. The LAT field of view is somehow smaller, but as you see, we have a very good view of the whole sky all the time in order to try to see if we catch gamma-ray bursts. Talking again energy range in order to find bursts, you see here I plotted the typical spectrum of a gamma-ray burst. And you see the energy range, so the peak of the spectrum, this yellow curve. I don't know if you can see my cursor here. I hope so. So here is the spectrum that peaks usually in the KV range, and here you have the GBM energy range that you see was really built in order to have it all, to be able to see it all. And here you have, for comparison, the BATSE instrument, which was, as I said, on the Compton Gamma Ray Observatory, the mission for gamma ray burst studies in the 90s, and I will use it as a comparison many times. And you have also the Swift satellite, which is also a dedicated mission for gamma ray burst study, but you see it's not really designed to catch the so-called peak of the spectrum of gamma ray bursts. So it tends to detect the softer events at lower energies. And the LAT, as you see, so when we first launched the mission, the question was, what will we see? Which kind of behavior will we see in gamma ray bursts at higher energies? So just a couple of more words about a typical gamma ray burst spectrum, because I just told you, okay, this is a typical gamma ray burst spectrum. So what is it? Basically, what we use to describe gamma ray bursts is a phenomenological function. So it is, you see, basically a broken power law with two energy indexes, low energy and high energy ones, and the so-called break energy. Actually, this is in photon flux. If you go to the nu spectrum, so if you look at the plot on the left, you go to the bottom panel. Basically, if you go to the SED, so to say, to the nu representation, you have the so-called peak of the distribution, and we usually use this kind of energy, which we call the peak energy, E-peak, to characterize a burst spectrum. This shape that was studied in the 90s, and it's still pretty valid until now, can be used both for describing, let's say, the whole GRB emission from the beginning to the end of what you measure in the KV, obviously. So the so-called time integrated spectrum. So the burst is long, I don't know, 5 seconds. You take it all, you fit it all, and you can describe your spectrum well. But also, if you go and split your burst, because as I told you, it can be very, very spiky, it has a very high variability during the burst, it can show many features. And the band function is a good function also if you go and, let's say, study your burst in time slices. So this is the so-called time resolved emission. So what is the physics behind? So this is a hugely debated argument. I was attending the latest gamma ray burst general conference in Japan in November last year, and still the mechanisms for explaining this kind of spectrum are highly debated. So there is an entire session only dedicated to people the theoretical, let's say, theoreticians fighting that their model is, let's say, the best to explain the gamma ray burst emission. So basically, what can we say without going in so much into the detail of different models? It's a non-thermal spectrum. There must be electrons accelerated in a magnetized region. So let's say, the most important mechanisms at play should be synchrotron. But again, the synchrotron has several problems. I don't want now to spend so much time and tell you all the difficulties of this scenario, but there are many other different flavors of this scenario to try to understand why, because the synchrotron alone cannot explain, for example, the low energy in some cases, the high energy at other cases, how much for example, the spectrum is sharp or broad. So there is really a whole world behind this, let's say, this topic. So let's just take as it is. I wanted just to show you what is behind the whole story of gamma ray burst models. So what did Fermi see over the 12 years? So as of today, we have 2,843 gamma ray bursts seen by Fermi GBM. In fact, this map that I show you here is the 10-year map that we just published a few months ago. in our fourth catalog of gamma-ray burst. You have long and short, you see in black and in red. And this is the important thing is that in January we exceeded the historical BATSE limits. So BATSE in 10 years in the 90s saw 2,700 bursts. Now we have, let's say, we went over this record, and we are now, let's say, the most prolific gamma-ray burst instrument in history, let's say. So we have the most events. As I said before, it's important the synergy between instruments. So we want to see how many bursts we see, for example, together with SWIFT, and you have here all of the detection that are contemporaneously. So with SWIFT, you see that's not so much. We have about 13% of so-called joint detections. The important thing about having joint detection with SWIFT is the position, because the localization possibilities of capabilities of the GBM are very low. So there are plastic scintillators. Our localization suffers from high systematics, so we can localize a gamma-ray burst to degree regions. So degrees for follow-ups are dramatic. So having a follow-up by an instrument, for example, like SWIFT, providing arc minutes positions is the key to have, for example, ground-based telescopes to follow you up. So this is crucial, is a crucial point. Also, Fermi-lat, now I will discuss it in a minute, is important to have let's say, much nicer positions, because with Fermi-lat, even if we have less detections, we have again arc-minute positions, so we can have an easier follow-up also in these cases. So just a few highlights from the, as I told you, from the catalogs by GBM. What we saw in all of these 12 years is that still all bursts come in two flavors, so short and long. This is the so-called bimodal distribution you see of all of our events. The duration of a burst is usually defined with the so-called T90. So this is how we call our duration. So it's the interval between the times where the burst reaches from 5 to 95% of the maximum fluence. And you see, of all our bursts, we have almost 20% of short gamma-ray bursts, and the rest are long gamma-ray bursts. So we basically detect much more long than short gamma-ray bursts. This is the rate. We have more or less 240 GRBs per year. This is, again, almost 200 long, almost 40 short. This is an important point, that GBM is a very good instrument for detecting short gamma-ray bursts. SWIFT is not so good in detecting short gamma-ray bursts. Why? Because usually short gamma-ray bursts tend to be harder in spectrum. So since SWIFT has a much softer, so it's a much lower energy range with respect to GBM, it detects less short. And why is it important? Because you all know that a couple of years ago, there was the huge announcements of the detection of a gamma-ray burst coincident with a gravitational wave, and this was short gamma-ray burst. So since then, short gamma-ray burst became much more famous and much more interesting for the whole community, because we have a whole program of observation together with LIGO and Virgo to hunt for gravitational wave events coincident with gamma-ray bursts, and so it's important that GBM is such a good short gamma-ray burst hunter. Regarding the spectrum, I don't want again to go into the detail. Here you have lots of distributions of the spectral parameters that I told you before, so alpha, beta, and the peak. These are a bit old results from 2014, but we have the newest let's say, catalog that is in preparation, that will be a 10-year gamma-ray burst catalog, in which we will present the distributions of, let's say, as I show you here, e-peak, and also the various spectral parameters. And this is important, again, to try to understand the model underlying the GRB physics, obviously. If we see that the band function is a good function, as I wrote you here on the left in this small panel, we wrote that the preferred model is Comptonized. What does it mean? So basically, I told you there is this high energy spectral index, which is called beta. So alpha is the low, beta is the high energy index. In many of the GBM bursts, we cannot constrain basically beta. So there is a kind of cutoff of the emission. And so this model with a cutoff, we call it the Comptonized models. And so in the majority of our bursts, it is very difficult to fully, let's say, go and fit to the very highest energies, and we need a cutoff to try to represent our spectrum. So following up gamma-ray burst, following up was in the first 10 years of the mission possible also on board, because we had, Fermi had the capability, which was called the autonomous repoint request, the so-called ARR, and we could repoint the LUT to follow up the brightest GBM burst. And this was amazing. We had more than 170 positive ARRs over the first 10 years of the mission. Then, unfortunately, in 2018, we had a problem with a solar panel of the Fermi spacecraft, and unfortunately, since then, we disabled these repoints. And so now we only see gamma-ray bursts at high energies with the LUT if the burst is in fact in our field of view, and if we can if we are following it during our sky scan in a usual way, but there is no, let's say, dedicated follow-up. This is a pity, because this kind of ARRs let us do amazing discoveries over the past year. The most famous LUT gamma-ray bursts, they are all, let's say, described in dedicated publications, because at the beginning every burst was better than the one before. And so here, so there are 35 gamma-ray bursts that are included in our first catalog that was published back in 2013. So it's an old catalog now. But as I said, these events all have single papers. So these kind of light curves that I show you here are the so-called multi-wavelength, multi-instrument, let's say, light curves. So you have the GBM on top at the various energy ranges, and the LUT burst in the bottom panels. And this is amazing, because you have to think that before the launch of Fermi, we were wondering if we could see gamma-ray bursts at such energies with so many high energy photons. As you can see, the red dots are basically the high energy photons themselves coming. And as you can see in both events, they are coming also when the low energy emission, the KV emission, is already over. So they are much longer at the highest energies. And this is even more amazing, because the two GRBs that I show you here, the one on the left and the one on the right, even if they look more or less the same, one is long and one is short. So if you take a look at the time scale, so one goes to 100 seconds and the other to a couple of seconds. So really, we could not, I mean, we were hoping for this, but it was a really exciting science. And if you want to read more, as I told you, these are the very first events, and they were published, one in Science, one in Nature, because they were really the bursts that we were expecting. And actually, they still are, both of these events are still record holders in their own, let's say, in their own characteristics. Because of how far, how energetic, how short they are, and they are still really very, very interesting events. The one that I told you before is the so-called monster burst. So this happened in 2013. This was the Science, let's say the Science cover. And this was incredible, because this was the first burst that saturated the GBM detector. So I don't know if you can have a feel here of the lowest energy. So this is the KV energies in the GBM. And as you can see here, the emission is almost cut. So the redshift was very low, so it was a very nearby event. It was extremely powerful. It had the highest fluence, the highest energy. It was the everything. And it has also one of the longest afterglow measured at high energies, and it was also followed up by optical, radio, instrument. It was really an amazing burst. And again, we went with several papers to Science. And the highest energy photon measured by LAT was a 95 GeV1, and this was the record holder for 10 years. So this was the motivation for Cherenkov telescopes to hunt even more closely gamma-ray bursts, because we knew there must be, and in this case, Cherenkov telescopes were almost there, because the Veritas telescope in the US was trying to follow it up. They had the full moon on the first night, so they had to wait for another night, and they came around. I don't know if you see here from, this is the light curve let's say in time of in the LAT energy range, but there was a Veritas follow-up at the very late times the day after, and they could place an upper limit, but they were not on time at the right moment. So this was really, let's say, a pity, because this was the perfect event for a very high energy, let's say, discovery. The newest, so I see that I am almost already, so it's already very late, so I think I will skip lots of slides. So let me just say something here. So we released exactly 1 year ago the second large GRB catalog. So we called it a decade of gamma-ray bursts observed by the LAT, and this comprises almost 200 gamma-ray bursts seen at the highest at the high energies with the LAT. I am very proud of this work, because I was one of the corresponding authors. So it was really a huge work that took almost 3 years to prepare, because it's not very easy to have a full, let's say, full picture of events that are so different from each other. I will go very fast through these slides. Basically, what do we study in this kind of catalogs? We study temporal properties and spectral properties as seen by the LAT. So we use the GBM information at low energies to somehow compare, but we didn't do an in-depth, let's say, joint study of the whole burst. So there is a whole work still to do in this respect. So we studied the properties of gamma-ray bursts at the highest energies, and we saw basically what we already saw in the first catalog. So the main characteristics are that the high energy emission is basically delayed with respect, so it starts a little bit after the low energy one, but it's extremely longer. So it's much longer. This is something that we saw in basically all events. And we have, as I marked here, so our longest burst, 130427A, the one that I told you before, the one in 2013, 34 kiloseconds. We have another one in 2016 that was 35 kiloseconds. So really they can really last for very long after the KV emission is over. So I will not go again into the detail of these events. Another thing that I want to say is that if you make a comparison of the brightness, so of the energetics that is between, let's say, what you can measure at low energy and high energy, what you see is that you expect to see the highest, let's say, the brightest events, the GBM, that are seen also by the LAT. What we saw in this study, in this systematic study, is that high energy emission is not always only bound to the highest energy events, but it can also come from weaker events. So we started populating, if you see here, for example, this plot here, but both of these distributions, one is the fluence and one is the flux, is that you are not only seeing with LAT the highest energy events, but also low energy events, and also short gamma-ray bursts that have a high energy emission. So this was a novelty. This we didn't absolutely expect. So I will skip all of this. I'm sorry, because it's really very, very late, and I want to finish with the highest energy events. So as I told you, record holder was this 95 GeV ones. Actually, in the 13/04/27 burst, we saw many events at these kind of GeV energies. And so we started in 2018, so when we prepared this kind of plots, we started to think about what can be seen at even higher energies, and we started to do this kind of studies of the distribution of the highest energy photons seen by the LAT, and to do prospects. So we use this kind of distribution to do the prospect for observation by let's say by Cherenkov telescopes at even higher energies. And while we were doing these studies, it happened. So the announcements of the breakthrough was done actually in November last year. And actually, we had two at the same time. So you are waiting 15 years for something, and then everything happens at the same time. This is always the case. So there were both collaborations, so the MAGIC collaboration and the HESS collaboration, that announced to have detected the very high energy emission from two different events. So I will try to be super quick on both events. So the MAGIC observation is, let's say, the most striking one, because let's say, it has a very high H.E.S., test significance value. So it's a very solid, detection, while the HESS event is seen at much later times, and it's only a 5 sigma detection. But both, let's say, both events were so striking and amazing that Nature decided to publish all together in the same issue. So if you're interested, and you go and see the volume 575 of Nature, you have all of these nice, wonderful publications that you can read. I will briefly show you some events. So basically, the MAGIC observation was amazing because of the timing. So you can see here, you have this is the light curve as seen by the SWIFT telescope that triggered together with GBM also. And you have to imagine that the alert was during the night. MAGIC is a Cherenkov telescope in La Palma, so it happened during nighttime in La Palma. They received the alert after 20 seconds. They started with the tracking and everything after 50 seconds, and they could stabilize the data settings after 62 seconds. So after 1 minute, and they discovered it. So this is after so many years. I mean, they were really hunting for 15 years such an event. It was a nearby gamma-ray burst, so there were for sure, and it was extremely bright. And this was, it was really the detection that the community was waiting since many years. And to have an idea of how bright the gamma-ray burst is for a Cherenkov telescope, here you have the photon flux above of the Crab Nebula. So, and I have again another representation here in which you see, I don't know if you see, if you listen, okay, there is also some audio behind this. But you have the seconds here. You see the timing goes by of how fast, or you have the accumulation of the counts by the Cherenkov telescope, and here you have the accumulation of the Crab Nebula. So this is how strong this event was seen in a Cherenkov telescope. So this, I mean, for me, it's absolutely amazing what they did here. We also analyzed the burst with Fermi in a very detailed way. We had let's say an ad hoc paper studying Fermi and Swift data to try again to understand the spectrum, how it evolves, and you can see. Oh, sorry. You can see here the different, so how you slice the event up, and you go and study the spectrum, and you can see the spectrum. I showed you the band function. You can see here the different components. You have extra components popping up at different times. So the amount of physics that you can do studying this kind of event was, again, really exceptional. and it was absolutely the second most fluent GRB detected by the lab. The first is still 130427. This was not the record holder, it was the second most interesting. And then here you have what I told you at the beginning, the multi-wavelength view of a gamma-ray burst. So here you have several instruments, Agile, Fermi, you have Fermi GBM, Fermi LAT, and on the right you have the light curve of this event, you have the magic data points in green, and then you have X-rays, you have radio, you have optical data, you have XMM, you have the full view of a gamma-ray burst during, you see here the time scale, here you go to 10 to the 6 seconds post trigger. So the follow-up in all of these wavelengths, and then also preparing, let's say, preparing this, putting together, as I said at the beginning, the community. So putting together all of these people that need to give you the data and put everything together, prepare plots, prepare the analysis. I mean, the whole work that is behind this it took a few months, as you can expect. And then you have to interpret. At the end, you have to understand why you have this kind of emission at the TV energies. And so you have, again, theoreticians trying to understand why you have this kind of model or why you have another one. And what you can see just as a pop-up here is you have two bumps. So what you can expect in your SED, you must have an extra component at the end. You must have some what we call the synchrotron self-conton. So you must have some photons that are contour up scattered, again, to the highest energies to try to understand, to put together what you see in the X at the same time at what you see at the TeV. And this is, again, in another, so this is the second publication. So there were several publications that explained each and every of these aspects. The other one, the magic detection, was, the HESS detection. This was an earlier burst, so this was in July in 2018, while the other one was in January 2018. This event, unfortunately, happened during daytime for the telescopes in Europe and in Africa. So the HESS telescopes are in Namibia, unfortunately. And so what happened? So there was a very nice detection by Fermi LAT, but you know, satellites don't have this problem about day and night. I was on shift that day, so I analyzed the burst, and the burst, I mean, it was a pity because we already didn't have this, you know, this system, this ARR, so we could just follow up the burst for 700 seconds, and then it went out of the field of view. And what happened? HESS followed it up during the night. So the burst happened at 12 during the day, and HESS had to wait 10 hours to have nighttime in Namibia to look at it. And basically, this is what you see. So after 10 hours, they detected a very faint source, as you can expect, because you have a delay of 10 hours, so it's a very long delay. But they detected a 5 sigma post-trial, let's see, UC source. And here you have a verification data set 18 days after the first detection. You can see it's compatible with background. And so you can say we detected this event. So here you have the only multi-wavelength light curve we have for this event with the poor data point after 10 hours that lies alone here, but with other data sets by Fermi, by Swift, some optical data. So you still can do what you saw before by magic, but okay, there is less information, but nevertheless, it's again crucial to try to understand what is the mechanism, if it is a simple synchrotron, or like the case before, if you have an SSC, again, to try to understand this emission at the very late times and try to understand if this TV emission is okay, I mean, it's compatible with what you see, for example, at the X-ray band at the same time. So it's always a game of trying to put everything together. So I'm sorry if I was a bit long. I come to my summary. So Fermi is active since 12 years, and it's still really constantly providing a great data set for GRB science. And both GBM and LAT are nowadays the most prolific GRB instruments in their respective energy bands, because we have more than 2,800 with the GBM, and more than 200 now with the LAT. So it's really big numbers. I know maybe people that are used to work with in AGN science, for example, they see thousands of sources, but for us these are really huge numbers. And as I said, the two key words are absolutely multi-wavelength and also multi-messenger. Today we didn't talk about the gravitational wave connection, but these are two key points to try to do follow-up campaigns. And I mean, follow-up campaigns are crucial because if you want to understand the models behind, the physics behind, you need to know what happens in another energy range. And it's always very tricky because I didn't go now into the detail of the LAT detections, but it's really tricky to simultaneously explain all of it, because if in one burst you say, okay, this model is fine at first and then, I mean, at different energies, then you find another burst and it's again different. It's again difficult to with the same model, you have to tune some parameters to try to explain it all. So to have a complete picture is also very difficult. And now we are starting with including the very high energy detections. So this is something, as I told you, relatively new. We had actually a new detection in August last year by the HESS. There is still no publication. The publication is in preparation. They are finishing. I hope that they will be publishing the paper in the couple of next months. Probably, I hope. And so, I mean, this is another very important confirmation that now that we really started, telescopes are improving their detection methods. They can, for example, they can follow up bursts even during full moon. So they are really improving over the years, everything from the techniques to the telescope itself. So what are we looking now forward? We are really looking forward to the next generation of this kind of instruments. For example, the CTA experiment, which will have much better sensitivity than the current instruments. So we really hope that we can boost this very high energy GRB detection, and even in case of, I mean, luck, even trigger on gamma-ray burst, even from the ground. So this would be the next step, let's say, let's go to the next level. So I hope that I interested you in this kind of journey. I will thank you and leave you with this artistic impression of the CTA experiment, and I am open for questions.
Thank you very much, Betta. Sorry, the clap is only virtual. Are there any questions? If you have questions, just raise. Jeter, go ahead.
Yes, thank you very much for the talk. I used to work on Cherenkov telescopes some time ago, about 15 years ago. So it's mine's mainly just a comment. It's really impressive to see, especially that plot you showed from MAGIC, how quickly it turned around. And I know all the technological innovation and design work that went into that. So that's really amazing to see. And congratulations to you and the team on MAGIC.
Yeah, it was really. I mean, I worked on this event from the Fermi side, but even, I mean, even witnessing something like this was extremely. I mean, we were all very excited because I have many friends that are part of the MAGIC collaboration, and I even know people that were sitting in the control room that day, and they could not believe. So at the beginning, they thought even it was a test by someone that was launching a test on something, you know, like a joke. And then they were looking at their screens and they were seeing the signal mounting. At some point, they said, okay, this is not a test, this is real. And they were, as you said, they were really waiting for many years because they started, I mean, MAGIC started in 2004. So the technological advancement was, I mean, they went from one telescope to two telescopes. So, okay. And then they changed the mirrors. I mean, they did a lot of technological improvements. And in this case also, they could look at this burst, even if there was, I don't know exactly now the percentage, but they had a high moonlight level. So really, it was an amazing achievement. Absolutely.
Are there any other questions? Like an heart attack when you're doing the shift and you see that, like.
Yeah.
Don't be shy. Karen, please go ahead.
Yes, hi. Well, thank you very much for your talk. Yeah, I kind of have like a general question. So I know the prompt emission in GRBs can accelerate particles, so we can produce neutrinos and we can detect those neutrinos with telescopes such as IceCube. Now that you have these really high energy photons in the afterglows, is it possible to accelerate particles at such stages like afterglows, or is maybe the optical depth way too thick and it's not possible to do so?
Well, I have to admit, I'm not an expert on this kind of let's say, of emission, but I know that there are, I mean, there are studies of prediction of neutrino emission from gamma-ray burst, and I think you can expect. So I am for sure, I know of the follow-ups by IceCube and Antares. I mean, there were several follow-ups of these two events, of 1901 14C and also of 1807 20B with no detection. But I mean, as far as I know, there could be. There is a problem of, how do you say, of distance, obviously. So it has to be not so far away. And in this case, actually, 1901 14C, so they were both relatively near. So if you have a nearby event, you have more probability of detecting it. So I know for sure there is a huge interest in catching neutrinos from gamma-ray bursts, and who knows? I am confident. I mean, I was also confident that we would see a TeV emission. So let's wait and see. As long as, I mean, as long as IceCube and the other neutrino detectors improve, probably, I mean, we will see what it happens.
Yeah, hopefully. That's what I do. So hopefully we will. Yeah, thank you.
Fingers crossed.
Any other question or comments? Doubt? We are very close to the hour. So if there are no more comments or questions, I would like to thank you very much, Elisabetta, for this very nice talk. And as soon as I have the slide, I will upload them. And thank you very much. And
thank you.